So first, I would like to thank for the invitation. And my name is Jiang Xiazi Lin, and I'm from Professor Liu Li's lab in Brown University. Today, my topic is spin orbit-driven ferromagnetism in magic angle twisted bilayer graphene. So first of all, I would like to thank my collaborators. This is Professor Liu Li and our students Erin and Zhi in the lab, and our theory collaborators Yahui, and the material providers from NIMS, Japan, and Columbia University. So first of all, I would like to give a brief introduction about his bilayer graphene. Here is the structure of a honeycomb lattice of a monolayer graphene, and here's the brilliant zone. It's the K and K prime.
Sorry, you're not sharing your screen yet.
Oh,
oh God. Oh, you do.
Yeah.
Sorry, there was a mistake on my side. Oh God.
Oh, it's okay now.
Go ahead. Yeah, go ahead.
Okay, great. And okay, great. And then this is a monolayer graphene. And then if you add the second layer of graphene to it and rotate it with a small twist angle, you will see this large long-range moire pattern, and this gives rise to a folded mini brilliant zone here. And when this twist angle is at the value of the magic angle, the theory predicts that the electron band will become extremely flat, like in this case. And in this case, the kinetic energy is quenched and the Coulomb potential energy dominates, and it gives rise to very strong electron correlation, and it gives rise to a lot of different emergent phenomenon that was not there for monolayer graphene. This is the band structure. The blue one in the middle is the flat band. The bandwidth is typically around 10 millieV. Here shows the measured conductance as a function of doping. You can see these two large gaps are corresponding to full filling of this flat band. In this system, there are 2 degrees of freedom, the electron spin, and the value K and K prime. Therefore, there are 4 degenerated flavors as K up, K down, and K prime up, and K prime down. Therefore, at this full filling, the density is corresponding to 4 electrons per moire lattice unit cell. And in this system, because the correlation is very strong, it gives rise to a spontaneous symmetry breaking of these 4 flavors. Therefore, within the flat band, at integer fillings of this moire cell, there will be additional insulating states called the correlated insulating states. For example, here is the half filling of the electron band. So the red arrows noted this correlated insulators that is arise because of the strong correlation. And the black arrow here is the insulating states corresponding to a single particle picture. And now we think what happens if we add spin orbital coupling to this strong correlated system. And we know that people have demonstrated a brilliant way of introducing spin orbital coupling into graphene by putting it next to a tungsten diselenide layer, for example, in this work. And the proximity-induced spin orbital coupling in the intrinsic bilayer graphene here results in this topological band inversion here. So here we use the same method to introduce spin orbital coupling in the magic angle twisted bilayer graphene. Here's our result. This picture is our tungsten diselenide approximated twisted bilayer graphene device. And here is the longitudinal resistance at low temperature. We can see the correlated insulating states here at the -2, 1, and 2, and 3 fillings of the moire lattice. When we apply a small out-of-plane magnetic field and sweep the carrier density forward and backward, we can see that there is hysteresis loop in the Hall resistance at quarter here and half filling of the moire flat band. And when we fix the carrier density at +2, the perpendicular magnetic field also induces the hysteresis switching here. And this hysteresis loop shrinks and eventually disappears above 7 Kelvin. This perpendicular field-induced switching is because the magnetic field opposed to the out-of-plane orbital magnetic moments. And since the tungsten diselenide has a relatively large band gap, it is insulating at low temperature. Thus, the influence on the twist bilayer graphene comes from the proximity-induced spin orbital coupling. And here, the Rashba term creates a coupling between the out-of-plane Valley index, and the in-plane spin index. Consistent with this picture, we observe the in-plane field-induced switching as plotted here. And here, this in-plane field first coupled to the in-plane spin magnet via the spin's demand energy, and then it couples to the orbital index via spin orbital coupling. Therefore, this in-plane field is indirectly switching these orbital magnets. And it's the direct evidence of the spin orbital coupling in this system. And next, let's look at the effect of a vertical displacement field. Thanks to our device structure of this dual-gated geometry, we can tune the carrier density and the displacement field individually. And here it shows the perpendicular field-induced hysteresis loop at half filling. The two panels are taken at the same density, but at different D fields. You can see the loop is bigger at positive D here and is smaller at negative D. And here we plot the coercive field as a function of D. We can see that for both quarter and half filling, the coercive field gets smaller as the D is smaller. And this can be understood as when the displacement field is positive, the electrons are pushed towards the tungsten iselenide, and the wave function between the twist bilayer graphene and tungsten iselenide is bigger, and the induced spin orbital coupling is stronger. And similarly, for negative D, the spin orbital coupling is weaker. And the stronger the spin orbital coupling, the larger the coercive field. And on the other hand, for the in-plane field induced switching, the displacement field dependence is drastically different. Here shows the in-plane field induced switching at half filling at different D. At positive D, the loop is counterclockwise, but at negative D, the loop changes sign. It becomes clockwise. We can also see this sign change from here, the coercive field plotted here. And as D varies, it changes sign for half filling, the blue line, you can see it changes sign. But for the quarter filling, the green line, it does not change sign. This can be explained by the calculated in-plane spin magnetic moment here. For quarter filling, the spin magnetic moment does not change sign, while at half filling, it changes sign with varying D. And the same sign change at half filling can also be observed here in the density-induced hysteresis. This displacement field dependence for both the out-of-plane field-induced switching and the in-plane field-induced switching is another evidence for the spin orbital coupling in this system. And to explain this unexpected ferromagnetism at half filling of this bilayer graphene, we propose a theoretical model that introduces spin orbital coupling in this system. According to this model, the spin orbital coupling breaks the C2T symmetry. And at half filling, with spin orbital coupling, it is energetically favorable to fill two bands at the same valley. Therefore, the total Chern number is non-zero in the case. It gives rise to the orbital ferromagnets. And the model also explains the in-plane field switching and the sign change by giving a valley contrast in-plane spin moments. And besides the ferromagnetic states at half filling on the electron side, we see this symmetry breaking at nu equals -1 on the whole side at zero external field. In twist bilayer graphene without tungsten iselenide, the insulating states at -1 here, as you can see, only appears at a high in-plane magnetic field. And this is reported by this work and by the Pomeranchuk effect. And here in our device, we observe a weak resistance state at -1 persists all the way to zero external field. We can see this symmetry breaking from both the peak in the longitudinal resistance, like in this map, and also in the density research in the Hall resistance density reset. And this additional observation also points towards the induced spin orbital coupling in this system. to summarize, we induce spin orbital coupling into a metric angle twisted bilayer graphene. And this induced spin orbital coupling drives the states at half filling into a ferromagnetic states. And we study both the out of plane field induced and in plane field induced hysteresis switching. And we also studied the dependence on the applied out of plane electric field. And also we observe additional symmetry breaking at the whole side, which is also pointing towards this effect of spin orbital coupling. And so that's all. I would like to thank my collaborators again, and thank you for your attention.
Thank you for the very nice talk. And again, thank you for giving it at such short notice. We're now open for questions, so please feel free to raise your hand or leave a question in the chat. But if there are none for now, I can start out with a question. So yeah, this is very interesting. I don't know too much about spin orbit coupling in twisted bilayers. So my question is that what other twisted bilayer systems like WSC2 or MOS2, would it be possible to show similar effects like this?
Yeah, it will be interesting to study similar effects in other twist systems too, because there are also like besides twisted graphene, like twisted other like semiconducting materials also possess this flat band. So it also has very strong electron correlation. So I would expect there are also very interesting phenomena like this in the other systems.
Thank you. There's another question in the chat. Oh yeah, go ahead, Alberto.
I mean, I was just wondering if there are any mechanisms to enhance the spin orbit coupling, either by, adding another van der Waals species to the heterostructure, or by trying to change the angle. I don't know. Any thoughts or ideas in that direction? Thanks.
Yeah, that's a good question. So according to what I know, like there is theory calculation shows that like the alignment angle between the tungsten selenide and the graphene can tune the strength of this induced spin orbital coupling, because like the atomic overlapping is different for different twist angle, not between the graphene, but between tungsten selenide and the graphene. So by this, there is a controlling knob that you can tune to get a stronger or weaker spin orbital coupling in this system. And also another experimental knob that you can tune this induced spin orbital coupling is by a pressure, because by adding a large pressure, you can actually press the graphene and the tungsten selenide closer to each other so that the wave function overlap is stronger. And there is another research, not in twisted, but in like intrinsic graphene, approximated to tungsten selenide. They use like hydraulic press to increase the overlap, and they do find that the induced spin orbital coupling, the effect is stronger when they are pressed together.
I see. Thank you.
May I ask a short question?
Yeah.
So,
Are
you running out of time?
Yeah. So could you leave the
sure.
just leave the question in the chat.
Yes.
Yeah, feel free to
Right.
send me email afterwards, or just
Yeah.
leave in the chat. Thanks for your questions.